How you doing, Professor?
Good. How are you?
Hanging in there.
Yeah, just a couple more weeks after this.
Professor, are you teaching any tech electives next semester?
I would like to, but we haven't gotten our schedule for the fall yet, and so I'm hoping that they're going to offer the finite element class 410, and so that's probably the most likely tech elective that I'll teach. Um, I think we're trying. I'm trying to get them to schedule 417 as well, which is computational heat transfer, and so hopefully those ones get scheduled, and then I'll probably end up teaching them. But as of right now, I think they're still trying to figure out the schedule and the teaching assignments.
Are those classes usually on a certain day, like usually?
So both of those classes are traditionally offered in the spring. So actually, I'm teaching them right now. But a lot of the feedback that I've gotten from students is that finite elements especially, would be more useful in the fall because that's then students would learn finite elements and then they can apply it for like senior design or formula or whatever their student projects are. And so this would be probably the first time in a long time we'd offer it in the fall. But traditionally, 410 is offered Tuesday and Thursday at 4 o'clock. Um, and then the 417 class is Monday, Wednesday at 5:30. But I don't know if we can still hold those time slots if we since the fall has its own schedule.
I see. Yeah. Amy recommended your I think it was computational fluids class. She
Oh,
really
okay.
liked it.
Oh yeah. That's a special class, and so that's the first time I'm offered it. But so that one I have no idea when the next time we're going to offer it. I'm hoping for next spring, but we don't know yet.
For the finite elements one, are you guys doing analysis on like different objects, or is it all medical based?
The finite elements is a lot more general, and so actually for that one I focus a lot more on structural mechanics stuff. And so things like a cantilever beam, and you load it with some kind of force or pressure, and you see how the thing deforms and how the stresses develop inside. I do a little bit of fluids in that one, but very very little. So the strong focus is on structures, and I do a little bit of heat transfer in that one too, but most of it is structures.
And then is it off of its own program, or is it with like SolidWorks?
It uses ANSYS actually. So ANSYS is the
Oh,
one
that's
that
right,
we.
ANSYS. That's what I meant,
Yeah, yeah,
ANSYS.
yeah. So ANSYS has a free student version. This semester it's been giving me a lot of issues. Like a lot of students have been having problems with it, and so I'm hoping by the fall that a lot of those will be sorted out. Um, but yeah, so that's kind of the main reason I use ANSYS because it's free. You can it's very limiting. You can't do much with it, but it at least lets us do the basics um, of finite elements with it.
Have you ever used OpenFOAM?
I haven't, but I'm gonna try to learn it over the last few weeks because for the 417 class, I don't have anything planned right now for I think the final 2 or 3 lectures, and so I'm hoping to learn OpenFOAM over the next week or so, and then teach it to the class, for then. But OpenFOAM is more focused on like fluids and heat transfer phenomena.
Yeah, I was I downloaded it and then I saw how much coding I had to do and then I got very discouraged. So
Yeah, it's a little bit intimidating. Yeah, so I have actually have no idea if I can learn it in time for the class, but I've used software as my kit, and so I'm hoping I can pick it up relatively quickly and write some tutorials for it. But yeah, that'll be my task for next week. Yeah, it's powerful though. I mean, it's nice because it's open source too, so you have full access to all the features in the code. It's not like ANSYS where you have to buy the license for it. So the fact that OpenFOAM is totally open, you if you can understand it, you can do almost anything with it.
yeah, I was on I think I was on Reddit and then they mentioned OpenFOAM. Like a lot of mechanical engineers recommended OpenFOAM because it's probably like it was the best software that they used. And then Dr. Mayral uh, suggested that too. So I tried to look it up, and then yeah, it was like coding is not my strong suit. So um, yeah, it was really hard to follow.
Yeah, it's yeah. If you're not used to yeah coding and writing like defining things in scripts and things like that, it can be really intimidating, especially if you're trying to learn on your own. So it's hard.
Which program are you guys talking about?
OpenFOAM.
OpenFOAM.
Oh, that sounds hard.
I mean, I guess if you can code, it's not that bad, but yeah. Um, the software is, I think it's all run on coding, right?
I
Or
believe so.
yeah.
I've only just taken very quick looks, and so I'm haven't really seen much. And then the all the YouTube tutorials for it are like 25 minutes long, and so
Oh yeah.
I just haven't had the time to kind of sit through like a long tutorial for it yet.
What's
Yeah,
the program
that's what
called?
I was trying to go on. I tried to look on YouTube and yeah, it was super long. And then they were just like they were going over really easy really easy analysis. So I can only imagine how hard it is if you wanted like a more complex structure.
What is the software name?
Open
Uh,
foam, FOAM.
yeah, I'll type
Okay.
it in the chat so you can see.
So, Edward, you were thinking of doing this for the to make up for the arrow?
Or was again?
Oh, for like
Um, well, kind of. I mean, so next year's formula team isn't going to have an arrow sub team because our roster's been cut. And it wouldn't make sense to have a arrow sub team, which I was interested in. Well, that was the sub team that I wanted to do. So I'm just gonna do like simple analysis on my own with another member. So I was looking into using OpenFOAM for that, but no, it was too hard for me.
You know, Eddie, if I put together some tutorials for it, I can forward them your way too, so you can take a look.
Oh, please, I would love that. Thank you.
Okay, yeah. Let me see if I can figure it out next week, and then anything I make, I'll send it your way. Okay, it's 2:30, so let's go ahead and get started today. All right, so good afternoon, everyone. How's everyone feeling today?
Good.
Good, good, good. Yeah, we're end of week 14, so after this we have 2 more weeks, and so starting including today, we have 5 more lectures to go. So very rapidly counting down. Okay, so I started grading your midterms this morning, and so I think I'm about 2/3 of the way done, and so I think I have about like 10 or 11 or 12 more of them to go, and so if your name is kind of in the first 2/3 of the alphabet, you I think you might be able to see your scores already and see the feedback. But if you're at the end of the alphabet, sorry, that's just kind of how it orders stuff. So, but I do plan on having those finished grading by the end of today. And so if I finish before I'm going to try to finish it before my 5:30 lecture today, but if not, it's probably going to be the first thing I do after dinner. So by end of the day, you should know what you got in the midterm, and I'll send an email out with the average and all that good stuff too. Okay. But so far looking pretty good. So you guys are looking, the scores are looking pretty good to me. Okay? But I'll have a full report, once I'm done grading all of them. So I don't want to say too much until then. Okay, so the plan for today is we're going to finish up, our first lecture notes on radiation. So, this one's kind of taken a little bit of time, but I think that's okay. And then after we finish that up, maybe about half the time, then we'll move on to the next set of lecture notes on radiation exchange. Okay. All right. And so I do have one more homework planned for this class, but I think I'll wait until Monday to assign it because a lot of it has to do with radiation exchange. Okay. Because so far all we've been doing is kind of just introducing the concepts of radiation and kind of just introducing kind of the general ideas. So we haven't really done much of what you can do to do problems yet. And so I'll wait until Monday to assign that homework. And then that last homework will be due on the Friday of week 16. And so 2 weeks from Friday, that's when it will be due. Okay, so there's just, at this point in the class, there's only just one more homework assignment and then the final exam. And those are the last two graded assignments that I'm going to give out. Okay. All right, so any questions I can answer before we get started? All right. Okay, so let's go ahead and pick up where we left off on Monday, right? And so we were going over this idea of radiation, okay? Okay. And in particular, we're looking at this, the fact that, because radiation acts on the same principles as light waves, right? It's basic electromagnetic waves. The amount of radiation emission power, okay, excuse me. Okay. The emission power for radiation depends on two primary variables. Okay. Okay. And so the first variable that it depends on is fairly obvious compared to everything else we've looked at in this class, and that's temperature. Right. Okay. And so the hotter an object is, the more radiation it's going to give off, and so that's consistent with everything that we've been doing in this class, right? But the other factor that it depends on, which really comes from the fact that it's an electromagnetic wave, is the wavelength of the wave. And the symbol we usually give wavelength is like a lambda, and temperature is T. Okay. And so in particular, what we said is that the total emissive power, which we call EBB, where the little bb stands for black body, okay, is equal to the integral from 0 to infinity. And so we're integrating over all the wavelengths times 2 pi h cross, which is, remember, Planck's constant, speed of light squared divided by lambda to the 5th power times exponential Planck's constant times speed of light divided by lambda kbt, okay, minus 1 d lambda, okay? And so what this represents here is the total emissive power integrated over all wavelengths. Okay. And you can see that just by the fact we're integrating from 0 to infinity. Okay. But a lot of times, we're not interested in all the wavelengths, all possible wavelengths. A lot of times we're only interested in just kind of a certain a narrow band of wavelengths. Okay. Okay. And so the way that we account for this is conceptually very simple, but mathematically very difficult to evaluate. Is that instead of integrating from 0 to infinity, what we're going to do is we're going to integrate from one wavelength to the other. Right, and so we have the exact same expression that we have up there, but our integration bounds are just going to go from instead of 0 to infinity, from wavelength 1 to wavelength 2, or in other words, lambda 1, lambda 2. Okay, and so remember the big difference here is that we're changing these integration bounds, okay? But everything else here is the same. So we have 2 pi, Planck's constant, speed of light squared, divided by m to the 5th, exponential, Planck's constant, times speed of light, divided by lambda kb t, okay, minus 1 d lambda. All right. And so this is how you modify the previous equation to only account for just a certain range of wavelengths, okay? And so in order to do this, all you have to do is just evaluate this integral. Although of course that's a lot easier said than done. And so, if you're particularly a masochist and you love doing math for hours and hours on end, don't let me stop you. You can evaluate this integral, and more power to you. But if you're like me and you see something like this with a lambda to the 5th on the bottom mixed in with an exponential term right there, that it's not going to be easy to evaluate this integral. And so thankfully the heat transfer gods also saw this. And so what they did was they evaluated this integral numerically, and they put a table together for you that makes it relatively easy to evaluate this integral. Okay, and so you would never actually evaluate this by hand. And so the way that you would do this is you would look at table 12.2 in the textbook. Okay, and then you can use that to evaluate this integral for you. Okay, although 12.2 it's not the most straightforward thing to use. And so on the next page I'll show you how you actually use that table to evaluate this integral. Okay. Okay. So any questions on this so far? Okay. All right. So let's look at table 12.2 in the textbook. And so I'll only write just kind of a small portion of it here, but the full table was of course in the textbook. Okay. And so table 12.2, it looks like this. So we have two columns. And so the first column is going to be lambda t, which is going to be the product of wavelength and temperature. And so the units for this are going to be micrometers Kelvin. Okay. Okay. And then the second column will be labeled with the with the capital F, and then in the subscript here, it'll say 0 to lambda. Okay. All right. And so let me start with the first column first. And so the first column is labeled in groups of 200 or increments of 200. So we have 200, 400, 600, 800, 1,000, 1,200. Do one more, 1,400. Okay. And of course, this continues on all the way up until Wien's law, which is almost 2,900. Okay. And on the right here, you have the corresponding numbers. And so it's going to be 0 for these first three. Okay. Then we have 0.000016. Okay. And 0.000031. Okay. Sorry, there's only 3 zeros for this one. Then we have 0.003134. Then we have 0.00779. Okay. And of course, this continues on. Okay. All right. And so the way that you use this table is that, remember we're performing an integral from a starting wavelength lambda1 and an ending wavelength lambda2. Okay. And so we want to perform our integral between these two values. Okay. And so the way that you use this table is that you take your two wavelengths. Okay. You multiply it by the temperature. Okay. And so you form this product of lambda t. Right. And then from this, you're going to get a number. Okay. And then from that number, you're going to read off the value of f from the table. Okay. Right. And so this is going to give us F1 and F2. Okay. So those are the capital F values for our first wavelength or our lower bound of integration. And F2 is our second value of the integral at the second wavelength. Okay. And so once you know F1, F2, then to compute this integral here, this E band, it's very simple. Okay? And so all you have to do is you take sigma, which is our Stefan-Boltzmann constant, you multiply by t to the fourth power, okay? And then you multiply this by the difference between F2 and F1. Okay? Okay. And that's it. Okay. So just to kind of summarize the steps. So if you want to perform this integral here at the bottom of this page, integral from lambda 1, lambda 2, first thing you have to do is you have to multiply each of the lambdas by the temperature in Kelvin. Okay, so it's going to give you lambda 1T, lambda 2T, right? From there, you look up in the table and see what the corresponding F values are, right? And so you're going to get F1 and F2 from that. Okay? Then once you have the Fs, all you have to do is just take the difference between the Fs. You do F2 minus F1, and then you multiply that by sigma t to the fourth, and that's going to give you your emissive power. Okay, for that band of wavelengths. All right, and so I'm going to do an example of this in the on the next page. But before we get there, are there any questions on this? Okay. All right, so let's do an example just to show you how this is done in practice. All right, and so in this example, we're going to consider black body radiation from a surface that's at 1500 Kelvin. Okay. And so the question asks, what is the emissive power corresponding to the geometry below, which I'm going to draw in a second. Over the wavelength band 2 micrometers to 4 micrometers. Okay. Right. And so this tells us our lambda 1 is equal to 2 micrometers. Okay. And then lambda 2 is going to be the upper bound, which is 4 micrometers. Okay. Okay. And so the geometry below looks like the following. So it's basically a cone. Okay. Okay. So we have a cone that's a hemisphere like that. Okay. Where this angle right here is 60 degrees. Okay. And the surface is here on the bottom, and the surface here is 1500 Kelvin. Okay, and so the first thing that we need to do is we need to find the area of this hemisphere, okay? Because the thing that we want to find out is basically the radiation heat transfer for this dome, okay? And so this is a little bit different than a full-on sphere, which is what we've done before. And so the first thing we're going to do here is compute the area of that hemisphere, okay? All right. And so to do that, we need to perform an integration here in spherical coordinates. And so we have a hemisphere. Okay. This is equal to, you can see here that theta is going to go between 0 and 60 degrees. And so the radian form of 60 degrees is pi over 3. Okay. Right. And so we're going to perform our integral. First, we're going to integrate over phi. And so phi is going to be this this direction here that's our polar angle, remember? And so phi, since we're doing kind of a full rotation around, that's going to go from 0 to 2 pi. Right? And then our integration over theta is going to be from 0 to pi over 3. Okay. And this is going to be cosine theta, sine theta, d theta, d phi. Okay. Right. And so, I'm just for the sake of time, I'm going to skip over the details of this integration, but this is a very classical kind of, trigonometric integration. And so the way that you would solve this integral is through u substitution. And so if you said u is equal to sine theta, okay, and then du is equal to cosine theta d theta. You would plug this into the equation, and then you would integrate the u, and then you do all that cool stuff. Okay, but for the sake of time, I'm just going to skip to the end because it's not really it's not a crucial part of this problem. And so what we get for the area of the hemisphere is 3/4 pi. Okay. Right. And so if you kind of recall from on Monday, when we look at kind of the whole entire hemisphere, we got an area of pi. And so this is about 75% of that. Okay. I drew this, not really to scale. And so I drew it kind of like a snow cone because I kind of want a snow cone right now. But 60 degrees is actually pretty big. And so, you probably the more realistic depiction of this geometry might look something more like this. Okay. Right. And so that's a little bit closer to 60 degrees. And so the fact that it's 3/4 of this, makes a lot of sense because the only thing that we're missing here is just kind of the stuff that's on the side. Okay. All right. And so now that we have the area of the hemisphere, we can go ahead and compute the banded emissive power. Okay, using the method that I talked about on the previous page. All right. So any questions on this so far? Okay. All right, and so now that we know the area, we can compute the banded emissive power. Okay. And this is going to be, first we multiply it by our area of the hemisphere, and so that's going to be 3/4 pi. Okay. And then we're going to integrate from lambda1, lambda2 of our big expression from before. So this is 2 pi Planck's constant, speed of light squared, okay, divided by lambda to the 5th exponential Planck's constant, speed of light, divided by lambda kb Boltzmann constant times temperature minus 1 d lambda. Okay. And so to evaluate this integral, we're going to do this via table. Okay. All right, and so to do that, we need to get the F values, or first we need to find the lambda T values and then the Fs. Okay? And so let's take our two lambdas here, and then let's go ahead and compute, let's multiply it by T and then get their values. Okay. All right. And so first we're going to compute lambda 1T. Okay. And so lambda 1, if you saw from the previous page, lambda 1 is 2 micrometers. Okay. So let's go ahead and plug that in. T in this case is 1500 Kelvin, and so let's go ahead and plug that in. Remember, whenever we're with radiation, you always have to work in kelvins, right? So no degrees Celsius here. Right? And so you perform that multiplication, you end up with 3000 micrometers K. Okay. Okay. And so now that you know lambda 1T, now you can look this up in table 12.2. Okay. And so for a lambda 1T of 3000, what we get is an F1 is equal to 0.273. Okay. And so that's the F value that's associated with our lower wavelength bound. Okay. Okay. Then we have lambda 2T. And so lambda 2T, we have 4 micrometers. Okay. Times 1500 Kelvin. Okay. We perform that multiplication, we end up with 6000 micrometers Kelvin. Right. Right. And then just like before, we're going to look that up in the table. Okay. We go to the row which has 6000 micrometers Kelvin, and then what we get is F2 is equal to 0.738. Right? And so now that we know F1, F2, then it's the E band here is going to be very simple. And so E band is going to be, first we have the area of our hemisphere. And so we have this guy that plugs in right here. And so we have 3/4 pi. Okay. Then we have the evaluation of the integral. So remember, with the F value is going to be sigma T to the 4th times F1, or F2, sorry, F2 minus F1. Okay. And so we plug all those numbers in, and conveniently, because this is a textbook problem, we end up with a total emissive power of 10 to the 5th watts per meter square. Okay. All right. Any questions on this example here? Right. So using the table to evaluate that integral is fairly straightforward. All you have to do is just take the product of the wavelength and the temperature, look that up in the table, get your F values, take the difference, and then multiply by sigma T to the 4th. Okay. All right. And so that's that's the basics of finding emissive power over a range of wavelengths. Let's see some other places where we can kind of apply these concepts. Okay. And so in particular, I want to talk a little bit about real surfaces. All right. And so this is kind of in contrast to our previous discussion, which we had, we were talking about black body radiation. Okay? And if you remember, for black body radiation, it's just kind of an ideal case where the emissivity and the absorptivity are 1. Okay? And so real surfaces aren't really like that. And so real surfaces have epsilon less than 1 and alpha less than 1. Okay. Right. And so this section here is going to be, how do we actually quantify these things, for a range of wavelengths. wavelengths. Okay, because in reality, you know, for real surfaces, the emissivity and the absorptivity, they're also going to depend on wavelength. And so, you know, we can actually use our integral from the previous page in order to help us evaluate this. Okay? And so, as an example, let's talk about just the emissivity. Right? And so, for the emissivity, epsilon, right? And so, if you remember the definition for emissivity, what it basically is a ratio of how much radiation this surface can emit relative to the black body, right? And so another way to kind of express the emissivity is the actual emissive power, right? And so that's the actual emissive power that the surface is giving off divided by the emissive power of a black body. Since the black body emissive power is the maximum, you know, you're always going to get an emissivity here of less than 1 for most, you know, for most real surfaces. Okay. All right, and so we can actually extend this. And so if we kind of take, you know, if we put these emissive powers in terms of our integrals here, okay, one way that we can express this is we can say the top here is the integral from 0 to infinity, or basically integral over all wavelengths of the emissivity as a function of lambda, okay, times E black body d lambda, okay, divided by integral from 0 to infinity EBB d lambda, okay. Right. And so in other words, you know, we can use kind of our integrals and our techniques from the previous page to compute kind of an overall emissivity for a surface. Okay. And so a lot of times we only just want to work with one value of emissivity because, you know, that kind of makes our calculations a lot simpler. But for most surfaces, you know, this emissivity here is going to depend on wavelength. And so all we're doing right now is we're kind of taking all those variations and just lumping it together into just one number that we can use for calculations. Okay? And so I'll show you what I mean by that in an example on the next page. But before we do that, are there any questions on this? Okay. All right, and so let's do an example here just to show you how it works. Okay, and so in this example, let's say that we have a surface that's at 1600 Kelvin. Okay. And its emissivity varies according to the following graph. Spelling is hard. Emissivity. Okay. And so we have a graph that looks like this. Okay. And so on the x-axis here, we have lambda, which is given in micrometers. Okay. And on the y-axis here, we have the emissivity as you know, that's going to change. Okay. All right. So let me draw 2 points here. And so we'll make a point at 2 and make another point at 5. Okay. And so this graph is going to vary like this. So we're going to go from here all the way up until 2. That's going to shoot up. And that's going to come back down. All right. And so this level right here is 0.4. And so this level right here is 0.8. Okay. All right, and so what we have for the surface is that for wavelengths that go between 0 and 2, then our emissivity here is going to be 0.4. And then for wavelengths that go between 2 and 5 micrometers, then we have an emissivity of 0.8. Okay. All right. And so from this problem, what we want to do is we want to compute a total emissivity over all wavelengths. All right. And so to do that, we're going to use the equation on the previous page along with all of our integrals and the table. Okay. All right. And so the total emissivity from the previous page is going to be equal to integral from 0 to infinity, okay, of epsilon of lambda, okay, times EBB d lambda, okay, divided by integral from 0 to infinity EBB d lambda. Okay. All right, and so now what we're going to do is we're going to split this integral up, right? Because what we have here is an epsilon of lambda that changes as a function of lambda, right? And so you can see here we have two zones. Okay. And so we have our first zone that goes from 0 to 2. Okay. And so this is going to be EBB of lambda d lambda, all divided by EBB. And so we know that we know from before that this integral here, this integral from 0 to infinity, this is going to be sigma TS to the 4th, okay? Because remember, that's the total emissive power over all the wavelengths. And so on the denominator here, we are going to have sigma TS to the 4th, okay? And then because in this region from 0 to 2, we have an emissivity of 0.4, we're just going to multiply by 0.4 out in front right here, okay? All right, and so we're going to do that, the same thing for the next band. And so the next band goes between 2 and 5. So up top, we're going to have integral from 2 to 5 of EBB of lambda d lambda, okay, all over EBB from 0 to infinity. And so this is going to be sigma TS to the 4th, okay? And then since in this range, the epsilon is 0.8, we're going to multiply a 0.8 out in front right here, okay? All right. And so this is nice because, you know, now that we have it in this form, you know, what we can do is we can look at these integrals here. And then what we can do is we can evaluate these integrals using table 12.2. Okay. Because what do we have in the problem? We have the temperature. We know the temperature is 1600 Kelvin. Okay. We know the wavelength bounds. And so the first one goes from 0 to 2. The second one goes from 2 to 5, right? And so we have everything that we need to evaluate these integrals. And then once we do that, we can just plug that into this expression here and get the total emissivity. Okay. All right. So any questions on this so far? Okay. All right. So let's go ahead and compute our products of lambda and t. Okay. And so first we have lambda 1 times t. Okay. And so lambda 1 here is 2 micrometers. Okay. T here is 1600 Kelvin. Okay. And so this gives us a value of 3200 micrometers K. Okay. Okay. As we look this up in table 12.2, what we get is F1 is equal to 0.318. Okay. Then we compute lambda 2T. So this is going to be 5 micrometers times 1600 Kelvin. Okay. This is equal to 8,000 micrometers Kelvin. Right. And so we look this up in table 12.2. And what we get is F2 is equal to 0.856. Okay. All right. And so now that we know our F values here, we can go ahead and plug them into our previous expression. Okay. All right. And so remember, we're trying to compute here the total emissivity, right? Right. And so the first term here is going to be the integral from 0 to 2, okay? And so the integral from 0 to 2 here is going to be F1 minus 0, right? Because the lower bound for the first integral there is 0. And so if you have a 0 wavelength, then that means that your F value is also going to be 0, okay? Okay. Then you multiply by sigma Ts to the fourth, okay? Then you divide by sigma Ts to the fourth, okay? Plus 0.8 times F2, because the second integral here is from 2 to 5. And so we're going to do F2 here, which corresponds to our wavelength of 5, right? Minus F1 times sigma Ts to the fourth divided by sigma Ts to the fourth as well. Okay. All right. And so obviously, you know, all these sigma Ts to the fourths are going to cancel out, right? And so you plug in all the F values there, and then what you get is a total emissivity of 0.558. Okay. Right. And now that we know the emissive power, then, or the emissivity, now we can compute the emissive power. And remember, we're working with a real surface here, and so it's not a black body radiation. And so the formula for emissive power here is going to be, normally we just take sigma Ts to the fourth, but you know, since we have this emissivity here, we're going to multiply it, okay? Right? And because our emissivity here is 0.558, that tells us that this real surface here is only emitting 55.8% of the maximum total power that it can do. All right, and so we plug in for emissivity, we plug in for the Stefan-Boltzmann constant, we plug in for the surface temperature, and what we get is a total emissive power of 207 kilowatts per meter squared. Okay. All right. So any questions on this? Okay. All right. And so in this example, you know, what we did was, you know, we took a case where, you know, our emissivity here changed as a function of wavelength. And then we use our integrals here to compute just a singular value for the emissivity. Okay. And so this same technique can actually be applied for absorptivity and reflectivity and transmittance as well. Okay. Because remember, you know, for real surfaces, you know, when you shine radiation on it, you know, it can do one of three things, right? It can either be absorbed, okay, which we give that the symbol of alpha, right? It can either be reflected, okay, and we give that the symbol rho, okay, similar to same symbol as density. And then the last thing it can do is it can be transmitted, or in other words, it can just pass right through your material, okay? And then we give that the symbol tau. And so for a black body, you know, what we have for that is we have an absorptivity of 1 and then reflectivity and transmittance of 0. Okay, so for a black body, we have perfect absorption. So any radiation that hits onto a surface, it just absorbs it and takes it in. Okay, but for real surfaces, you know, it's not really like this. Okay, and so the way that we can compute these is, you know, very similar to, you know, what we did before. And so the formula for that is basically the same as emissivity. Okay. Except the only difference here is that now we have alpha of lambda instead of epsilon of lambda. Okay. For reflectivity, we have the same thing. Okay. And then for transmittance, we have the exact same thing as well. Okay. Okay. And so anytime you have one of these properties, either emissivity, absorptivity, reflectivity, or transmittance, okay, if at any time these guys change with the wavelength, which in most cases they do, in order to evaluate their actual values, you know, all you have to do is just kind of use this integral here. Okay. Okay. And so you know, I do have one more example of this in the lecture notes, but and so you can check that out if you want to see this this in action one more time. But you know, because we did the last example and it's kind of very similar to that, I'm going to go ahead and call this one right here and then move on to the next set of lecture notes, which is on radiation exchange. Okay. And so, are there any questions on this before we move on to the next set of lecture notes? Okay. All right, and so that's our introduction to radiation. And so you know we picked up a lot of new terms here. It's a lot of new constants, and so you know radiation is quite different from the other two forms of heat transfer. Okay.
Professor?
Yep. What's up?
Just to make sure it's d lambda, right, not dx.
Yes, it should be d lambda. Yes. Yeah. So you're integrating over the wavelength. Mm-hmm. Yeah. Thank you for that. Mm-hmm.
Thanks.
All right. And so now that we kind of have, you know, all these kind of basic concepts of radiation, I say basic, but you know, it kind of feels like a whole new language compared to all the other heat transfer that we've done. But now we kind of have the building blocks that we need to, you know, kind of really start to look at some real kind of heat transfer problems with radiation. Okay. And so our first step in this is going to be called radiation exchange. Okay. All right. And so, you know, up to this point, you know, we've seen that, you know, as long as a surface has some kind of temperature, it can both emit and receive radiation. Okay. Okay. And it's always doing this, right? So any object that you see around you, you know, it's both emitting radiation and it's also taking in radiation from, you know, all the other sources of you know, around it. Okay. And so, you know, constantly at every single, you know, points in time, you know, all objects here are basically radiating and receiving, you know, radiation, you know, constantly. Okay. Okay. And so, you know, and so what we're going to cover here is, you know, how do we quantify this? And so how do we quantify, you know, the fact that, you know, we have two objects. And so, you know, if you have two objects in space, one object is going to radiate the other one and then the other object is going to radiate back to the first one, and then those are going to be absorbing those radiations as well. Okay, and so the whole idea with this unit here is, we want to cover how objects exchange heat with each other through radiation. Okay. And so this is not that much different than than just all the other heat transfer that we've covered, right? And so let's take conduction as an example, right? And so if you say, let's go ahead and take an ice cube from your freezer. You don't have to do this, of course, but if you take that ice cube and you hold it in your hand, right? You have two objects here. So you have your hand and you have the ice cube, okay? And because there's a temperature difference in between them, naturally what we expect is that there's going to be some heat that's going to be exchanged through them via conduction. And so so this idea of radiation exchange is the same thing, but instead of conduction, we want to see how different surfaces or different objects exchange heat with each other through radiation. Okay. All right. And so the unfortunate thing is, we can only handle very simple situations because, once you start getting into complex geometry or, multiple objects and, real surfaces and all that stuff, it gets complicated very, very quickly. Okay. And so we're going to need to work with a lot of assumptions to kind of simplify this analysis for us. Okay. And so the first kind of concept that I want to go over, which is kind of I think the simplest concept of radiation exchange, is called Kirchhoff's laws. I don't know if this is the same Kirchhoff as the circuits guy, but and so it might be. He might have just been a busy guy. Okay. So I think usually when you say Kirchhoff's laws, I think most people normally think of circuits, but this is radiation Kirchhoff's law. Okay. All right, and so for this situation, we need to come up with a very contrived situation, and so this is something that's kind of hard to do in practice, right? And so to illustrate this law, what I want you guys to imagine is a closed cavity with an object that's magically levitated within. Okay. And so let's say our closed cavity looks like this. Okay. It can really be any shape, and so I'm just going to draw it to something like that. Okay. The important thing is that it's closed. Okay. Oh, it is the same Kirchhoff. Wow, what a busy guy. He did circuits and radiation at the same time. And so the surface, the enclosing surface, it doesn't really matter how it's shaped. The important thing is that it's closed, right? And so think of like like a Christmas present, right? So before you open the Christmas present, it's covered all the way around with wrapping paper, right? Okay. And on the inside here, we're going to have some object, and this object somehow is magically levitating with it. Okay. All right. And so, inside this closed enclosure here, both the surface and the object are going to be radiating heat. Okay. And so we can illustrate this with with arrows. Okay. And because it's enclosed, what's going to happen is that the heat is going to basically kind of bounce all the way kind of around. Okay. Right? And so that might be like a radiation ray from the surface, but of course the object here will also be radiating. Okay. And so basically there's no way for radiation to escape. Okay. All right, and so let's define some temperatures here. And so let's assume that the outer surface has a temperature of Ts, okay? And then the spherical object on the inside, we'll call that T1, okay? And for now, we're going to assume that they're different temperatures, but later on we'll relax that assumption, okay? Okay. All right, so any questions on the setup for Kirchhoff's law? Okay. All right, and so just like I mentioned previously, because it's a closed cavity, okay, no radiation can escape. Okay. And if no radiation can escape, what this means is that eventually any radiation that gets emitted has to be absorbed at some point. Right. There's no other option for that. And so the radiation just doesn't keep bouncing and bouncing and bouncing around. Eventually it has to be absorbed. And the absorption can either it can either be done by the outer surface or it can either be done by the object. Okay. All right. And so because all radiation is absorbed eventually in the cavity, what we basically can say is that the absorptivity or our alpha value inside the cavity in total is going to be 1. Okay. And 1.0 is the highest possible value of our absorptivity. Okay. And what do we know about objects that have an absorptivity of 1? They're basically a black body. Okay. And so what we can say is that the irradiation, G, okay, this has to be equal to the black body emissive power for the temperature Ts. Okay. Right. And so the irradiation, or in other words, all of the radiation that gets absorbed has to equal to the black body emissive power. Okay. Because now we're assuming that the cavity acts like a black body. Okay. So any questions on this so far? Right. So notice how up to this point, I actually haven't told you anything about the surfaces of the object and the walls, right? And so the object and the walls could actually be real surfaces, but because it's a closed cavity, very tightly closed, even if it's a real surface, it essentially acts like a black body because everything has to be absorbed eventually. Okay. All right. And so now let's make an additional assumption. And so now let's assume that we're at steady state. Right? And if we're in steady state, then what that tells us is that we've achieved thermal equilibrium. Okay. And thermal equilibrium basically essentially means that the surface temperature and the temperature of the object are equal. Right? And so, everything here is going to be at the exact same temperature. And so all the radiation that comes out is going to be equal to the all radiation goes in. Okay. Okay. And so these two rates basically have to be the same in order for us to have thermal equilibrium. Okay. All right. And so let's take this conclusion here, where there has to be a perfect balance between radiation out and coming in, and let's apply that to the object. Okay. Right. And so in other words, we're going to draw a control volume around the object, and we're going to set equal the radiation that's emitted and the radiation that's coming in. Okay. All right. And so the radiation that's emitted is going to be the emissive power at this temperature, okay, at Ts times A1. Okay. This is going to be equal to alpha 1 G A1. Okay. Where on this side of the equal sign, on the left side, this is the total amount of radiation going out, or the amount of radiation emitted by the object. Okay. And then on the right-hand side here, we have the radiation that's absorbed by the object. Okay. And we have to say that, these two things have to be equal to each other because of our thermal equilibrium. Okay. Okay. And so, first thing we're going to do, we see that we have A1 on both sides. And so we're going to cancel that out. So that's just the surface area of the object. Okay. And so now what we have is E1 at Ts is equal to alpha 1 G. Okay. And so what we're going to do next is we're going to plug in for G, and we're also going to plug in for E1 here. Okay. And then we'll get kind of an important definition that we're going to use going forward. Okay. So any questions on this so far? Okay. All right. And so from here, we're going to take G and plug in from before. Okay. And so just from the fact that we know that G here is going to be the same as EBB at TS. Okay. Right. And that comes from our assumption that, everything gets absorbed eventually. And so the irradiation, G, is going to be the same as the black body emissive power. Okay. Next thing we're going to plug in is E1 of TS. Okay. And so this right here represents the real emissive power. Of the object. Okay. And since it's real, another way that we can express this is the emissivity times the black body radiation at TS. Okay. Right. Because remember, emissivity is basically the fraction of the total emissive power that this object emits. Okay. All right. And so let's go ahead and plug in for both of these into this expression here. Okay. And so if we plug both those in, on the left-hand side, we have E or epsilon times EBB of TS, okay? And on the right-hand side, we have alpha times EBB at TS, okay? Okay. And so we see that the EBBs cancel out, okay? Right? And so what we get, which is a very nice assumption here that we can make, is that the emissivity and the absorptivity are equal. Okay. And so if you have an object that's enclosed in a closed space, then by Kirchhoff's law, then the emissivity and the absorptivity have to be equal to each other. Okay, and it doesn't matter, what properties the object has or what kind of surfaces. And so you could have like a mirror ball, you can have a mud ball, you can have your phone, you can have a glass of water, right? It doesn't matter. And so no matter what, as long as that object is in enclosed surfaces, the absorptivity and the emissivity are going to be equal. Okay. And this is really nice, because if we could assume this for for all surfaces, it's going to make our lives a lot easier. Okay. Right. Okay. So any questions on this so far? Okay. All right. And so we just went through that derivation of Kirchhoff's laws, and we saw that it only applies for an object in an enclosed surface. Okay. But it would be really nice if we can apply this for more surfaces. Okay. And the nice thing is that if we make some assumptions, we can actually apply Kirchhoff's law to all other surfaces. Okay. And so the question now becomes, when can we apply Kirchhoff's laws to just a regular object? Okay. And so the answer to that is, we have to make some assumptions. Okay. And so the next section is going to be titled gray surfaces, which is kind of gives you the hint of when we can apply these. Okay. And so I say gray surfaces, but I don't literally mean the color gray. Okay. And so just like previously, we used the term black body. It doesn't actually mean that the object is the color black. Right. It's just, it refers more to its radiation properties more than anything. Okay. And so a gray surface here just has to do with its radiation properties. It doesn't really have much to do with the color. Although I think that the actual color gray does share these qualities, but you can achieve these qualities without being the color gray. Okay. And so basically, we want to answer this question here. When can we apply Kirchhoff's laws, or in other words, when can we assume that absorptivity and emissivity are the same? And so the first condition is that we have kind of two conditions here, okay? And so of these two, only one of them has to be true. Okay? Right? And so the first condition is that the irradiation is diffuse. Okay? Okay. And so diffuse is a new term here. And so diffuse, all that means is that it's independent of direction. Okay. In other words, the irradiation doesn't depend on theta and it doesn't depend on phi. Okay. All right. And so that's the first. That's the first condition. So the irradiation basically means that the radiation waves themselves are diffuse and they don't depend on theta and phi. Okay. And so the other condition is that the surface that's being irradiated is diffuse. Or in other words, the surface itself, the surface itself doesn't matter which direction it's being irradiated on. It's not going to matter. Okay. Okay. And so what this basically says is that alpha and epsilon for the surface are independent of theta and phi. Okay. Right. And so it's a bit hard to kind of describe these these conditions here kind of in more detail without really getting into the weeds. But I do want to say that either of these assumptions are pretty reasonable. And so for most engineering applications, it doesn't really matter which direction the radiation is coming from. It's still going to be radiation all the same. Okay. And so it's kind of more in kind of these more niche kind of laboratory situations where you would probably violate either of these, but assuming that either the irradiation or the surface is diffuse is usually pretty reasonable for most materials. Okay. Okay. Any questions on this so far? Okay. All right. And so this is the first condition that has to be satisfied. And so either one of these can be true. Okay. In addition to that, it has to satisfy one more condition. Okay. And so this is kind of like the last one too, where I'm going to give you two, and only one of them has to be true in order for Kirchhoff's law to apply. Okay. And so the first condition is the irradiation on surface comes from the emission of a black body. Okay. Right. And so if the radiation that's hitting your surface, if that came from a black body, then that's good enough. Okay. And so the other condition is that the surface itself, the one that's being irradiated, that is gray. And so what that means is that alpha and epsilon, or the absorptivity and the emissivity, are independent of wavelength. Okay. Right. And so that's what a gray surface means. And so if you have a gray surface, all that means is that your absorptivity and emissivity, they don't depend on wavelength. And so it's kind of the opposite of the situation for all the examples that we did kind of before this, where, you know, we had that emissivity change as a function of wavelength, right? And so if a surface is gray, it just means that alpha and epsilon are the same at every single wavelength. Okay. And if you can satisfy these assumptions, then you know, you can apply Kirchhoff's laws. Okay? All right. And so, you know, if you compare these next two conditions to the first two, you know, these two are actually a little bit harder to accomplish in practice. And so, you know, in order to assume these, you have to make some pretty big assumptions. But when you do, it actually does save us quite a bit of time. All right. So, any questions on any of this? Okay. All right, so we have about 1 minute left, and so the next thing in the notes is an example, but I don't really want to start it now and then kind of just cut it off after a minute. And so we'll pick this up on Monday, and then we'll do that next example, right? And so so thank you guys for tuning in today. Hope you guys have a good rest of your evening. Hope you guys have a good weekend, and I'll see you guys on Monday.
Have a good week, Professor.
Thanks, guys.
Thank you,
Yeah,
Professor.
have a good weekend. David, Isaac, could you have any more questions? Okay. All right. So if there's no more questions, I'm going to go ahead and sign off. And so have a good weekend. I'll see you guys next week.